Well, hi everybody. I want to step in here and give you a little bit of a talk about, well, what ultimately is one of the most important things about a vector space, which is to try to find a basis for that vector space. In order to get to that material, let me set things up with some notation here. Let's let V be the vector space that we're looking at. And imagine we take a handful of vectors out of V. V1, V2, up through Vk. There are two important questions that we would like to ask about that set of vectors. Both of them are yes-no questions. Okay? The first one is, do those vectors form a spanning set for V? Okay? Let me just remind you that this just means, a spanning set just means that if you take the span of all of these vectors, V1 up through Vk, right? That the span of those vectors is the whole vector space. Okay, that's what a spanning set is. It's a set of vectors that spans the whole vector space. And we've talked in the past, I have a separate discussion and a separate video about how to find a spanning set and how to test if something is a spanning set or not. Okay? The second question we want to ask about our vectors is, are they linearly independent? Okay? Because we don't just want to span our vector space. We want to do it efficiently. Right? Imagine that every vector that you put into your spanning set is expensive. It costs you a lot of money, right? So we would like to span our whole vector space as cheap as possible, right? Using as few vectors as possible. Well, these are the two main questions we want to address. And I'm just going to go ahead and spoil the fun now and let you know that if the answer to both of these questions is yes, then your set of vectors is what is called a basis. Okay? So a basis for a vector space V is a set. Okay, so I'm just going to use the same notation, V1, V2, up through Vk, such that, well, sorry, it's a set that is linearly independent and spans V. Okay, so in other words, the answers to these two questions that we were just asking are both yes. Okay, so these are very important questions that we want to try to answer, these two questions. And if both of them turn out in the affirmative, if we have a spanning set and it's also linearly independent, then it's what we are going to call a basis. Okay, now what we have seen, what we have recognized is that to answer the first question, what I have to do, sort of from a practical and procedural point of view, is lay my vectors into the columns of a matrix. And I'm going to augment this matrix with a column of what I'm going to write as number symbols, because you're going to basically be putting coefficients of a generic vector in that far right column. Right? So it could be like XYZ or ABC or whatever. And as you do elementary row operations on this matrix, those expressions in that far right column just continue to be expressions that involve those variables. What those actual expressions are doesn't really matter. So that's why I'm abbreviating that far right column with just this number symbol notation. Okay? So that is how you check if a set is a spanning set. But as it turns out, to test whether that same set of vectors is linearly independent, you're going to essentially do exactly the same thing. You're going to lay your vectors out into the columns of a matrix again. The only difference is this time you're going to augment with a zero vector. Okay? And now, what are the conclusions that you're going to draw? In both cases, you're going to do row operations. And you can really essentially just do them once because it's the same matrix more or less, right? So you can just do the row operations on this matrix, reduce it to row echelon form. And what are we looking for? Well, in the first case, if the matrix ends up with a consistent system, if there is a solution, then the answer to the first question is yes. And if the first matrix leads to a pivot in the far right column, that would be an inconsistent system, then the answer to question number 1 is no. So it's very simple. Take your vectors, lay them into the columns of this matrix, row reduce the matrix, look at your pivots. As long as your pivots do not drift into that far right column, right? If they do not go into that far right column, that's a good thing. It means your system is consistent, and the answer is yes. Okay? Otherwise, the system is inconsistent, and the answer is no. In the case of the linear independence question, it's not so much whether the system is consistent or not that we care about. And in fact, the second matrix here is always going to be consistent because the far right column is just all zeros and will always be all zeros, right? There's never going to be a pivot in this far, far, far right column over here. So I don't care so much about consistency. What I care about this time is whether there are free variables or not. And if there are no free variables, which means that basically there is one unique solution to your linear system, then that means, yes, your system is linearly, or sorry, your vectors are linearly independent. But if you end up with free variables, that is the situation of no, where your vectors are not linearly independent, which of course just means that they are linearly dependent in this case, right? So if there are free variables, then that's a bad thing in a sense. It means that the vectors in your set were LD. Okay, and in fact, you can use the free variables to sort of represent the linear dependency that is there. Let me give you an example of this. Okay, so let me come back over here and let's just try an example. Okay, so for example, suppose I take V to be P3 of R. Okay, and I'm going to take my set, I'll call the set S here. It's just a set of vectors. I'm going to use a 1 plus x, 1 plus x squared, 1 plus x squared plus x cubed, and x plus x cubed. Okay? And let's try to answer the question, is S a spanning set, Li, both, or neither? Okay? So let's try this example. This is a great classic sort of example that we can try to get the idea behind this. Okay? Well, for answering both of the two questions, the spanning set question and the linear independence question, I'm just going to build this matrix right here. Okay, so in the first column, I'm going to put the first polynomial, which is just a constant polynomial of 1. It does not have an x or an x squared or an x cubed coefficient, so I'll put zeros down the rest of that column. The second polynomial, 1 plus x, would be represented as a 1, a 1, a 0, and a 0, right? So I'm kind of putting my constant coefficients in the first row, my x coefficients in the second row, and I'm going to keep going like that, x squared and x cubed. The third polynomial would look like that, right? 1 plus x squared. 1 plus x squared plus x cubed would look like that, with a 1 in every single row of that column. And x plus x cubed would be 0, 1, 0, 1, like that. Okay? And I am going to augment this matrix with, I'm going to kind of kill two birds with one stone here. I'm going to augment with both the number symbol and the zero vector kind of at the same time so that I can address this question kind of all at the same time. Okay, so we kind of have two scenarios going on. Well, the cool thing about this one is it's already in row echelon form. And I want to focus on talking about the conclusion of what we're going to say based on this row echelon form anyway. So we'll kind of avoid having to do any hard work to get to the punchline here. Now what you'll notice is that no pivot made it into the far right column. It means it is consistent, right? It is a yes on the consistency question. Okay? However, there is a free variable right here. By the way, the variables, these are those constants that are in the definition of linear independence, C1, C2, C3, C4, C5, right? So C5 is free, right? C5 is a free variable, so we do have free variables, so that puts us in a no scenario here. So the correct answer is that this set of vectors is a spanning set, but they are not linearly independent. What that means is that one or more of these 5 vectors can be written in terms of the other vectors. Okay? Maybe we want to know how that's possible or how that would look. So let me talk about that. What we can do is actually solve this system and figure out from the free variables what this linear dependency looks like. So notice that C5 is a free variable. I'll call it T. And from that last row, C4 plus C5 has to be 0. So if C4 plus C5 is 0, then that means C4 is negative T. From the third row, I see that C3 plus C4 has to add up to 0. So C3 is also T. And from the second row, I see that C2 plus C3 plus C4 plus C5 has to add up to 0. So if I have to have all 4 of these expressions adding up to 0, you can pretty quickly tell that C2 has to be negative T. And then finally, C1 plus C2 plus C3 plus C4, that also has to add up to 0. So if you just look at the first 4 variables and think about what C1 has to be, you see that it equals T. Now, I can choose any number I want for T. But when I'm trying to exhibit a linear dependency, what I'm going to want to do is choose a T value other than 0. I'm going to choose 1. You want to choose a T value that's other than 0, because if T is 0, all of your constants would be 0, and you're not going to create an equation that gives you a linear relationship among the vectors, right? So let's choose T to be 1. It just means that C1 is 1, C2 is negative 1, C3 is 1, C4 is negative 1, and C5 is 1. And all that means is that if we take 1 times V1 minus 1 times V2 plus 1 times V3 minus 1 times V4 plus 1 times V5, that should cancel out to 0. Okay? That's what should happen. And in fact, it is pretty easy to see that that's true. If we solve this equation right here for V5, right, notice that what we'll get is V4 minus V3, and then we'll also get V2 minus V1. Well, if you look at V4, so this is V1, right? V2, V3, V4, and V5. If you look at V4 minus V3, V4 minus V3, well, that's exactly x cubed. And V2 minus V1 is exactly x. So sure enough, that's what V5 is, right? So this is what we call, or this, either one of them really, these are called linear dependencies, right? So you're writing down a linear dependency in this case. It's a linear dependency. Okay, so let's try another example to see if we can practice this a little bit more. This is an example involving polynomials, okay? So let's do another example of this. So from a calculational point of view, we kind of do all of these problems by just setting up a matrix, right? It's just a matter of setting up a matrix here. Okay, so let's do this one. Following example here is the set 1, 1, 0, 0, 0, 1, 1, 0, 0, 0, 1, 1, and 1, 0, 0, 2, a spanning set for R4? Is it Li? Is it both? Or is it neither, right? So these are the kind of questions I like to ask in Math 250B. Okay? Or in the theory of vector spaces more generally. Okay, so for the solution to this, I'm just simply going to arrange my vectors into the columns of a matrix again. So I'm going to make columns here like this. Notice that even though the vectors were given to me as rows, I still need to lay them into the matrix as columns, right? And I'm once again going to augment with either number symbols or zeros. Okay, depending on whether I'm focusing on the spanning question, right? That's where the number symbols come from. Or if I'm focusing on the linear independence question, which is where the zeros come from. Now this time the matrix is not quite in row echelon form, so let me go ahead and work on that a little bit. So the first row, of course, is going to stay the same. But I'm going to take the negative of the first row and add that to the second row. So if I do that, I'll get 0, 1, 0, negative 1. And see this number /0 option over here never changes. Okay, never really going to change. I'll leave the third row alone for a moment. And I'll also leave the fourth row alone for a moment. Okay, so let's just keep going. We're not quite there yet. We have a pivot here, and there's a pivot, but I need to take the negative of the second row and add it to the third row. If you're watching this in detail, you don't maybe need to write down all of these steps. You can just enjoy watching me do them. It's really the punchline at the end that I'm going to care the most about. So I'm going to do the negative of the second row and add it to the third row here. And then I'm going to leave I'm going to leave the last row the same. And then one more step. I think we are just about there. So I have 1, 0, 0, 1 with a number or a 0. And then I have 0, 1, 0, negative 1 with a number or a 0. 0, 0, 1, 1 with a number or a 0. And I'm going to take the negative of the third row and add it to the fourth row. And sure enough, I get pivots right down the main diagonal. So no pivots drifted into the far right column. It means this is consistent. And that means that my vectors are in fact a spanning set for R4. On the other hand, there's no free variables to the left of my augmentation bar, so all of my constants, right, in this case, the only way that I could solve that system with the zeros on the right-hand side would be to choose those constants to be 0. Okay, so there's no other way to do that. So this is actually both. This is actually both. And in fact, that means, let me just remind you, that means that this is a basis for R4. We have a basis for R4 here. We have exactly a linearly independent set of vectors that spans our space. We have spanned R4 as cheaply as we could. Okay. Now, what you might remember is that the fact that we have pivots going right down the main diagonal of this square matrix, right? The pivots are going right down the main diagonal here. It just means that the original matrix was invertible. And if I had wanted, I could have, because it's a square size matrix, I could have just taken the determinant of that matrix and I would have known that my pivots would look like this. Okay? So I chose to do the EROs, right? The elementary row operations. It wasn't too bad. But if you didn't like the elementary row operations, you could have instead just taken the determinant of this matrix. And that would have been good enough. Okay? Great. Let's do another example. If I'm going too fast, just pause me and copy down whatever notes you need. You can certainly catch up easily enough when you have that option, right? Okay, So let's do this. Let's do this example here. I'm going to take V to be R3 this time, and I'm going to take my set of vectors to be 1, 1, 1, 2, 0, 6, and 4, 2, 2. Okay? And I'm going to ask the same question. Is this a spanning set for R3? Is it linearly independent? Is it both? Is it neither? Right? Okay. So, as usual, I'm going to do this one quicker. We're going to put this set of vectors into the columns of this matrix. Now, I'm going to stop right here, because I notice already that I have a square matrix. Okay? So if I learn the lesson from the last example, right, it's that if I have a square coefficient matrix, then instead of augmenting the matrix and doing elementary row operations, I could just take the determinant of this and figure out what is going on. It turns out that the determinant of this is not 0. Okay? And if the determinant is not 0, then I know that my pivots are going to go right down the main diagonal. Nothing is going to end up in the far right column, and I will have no free variables. It means it's a basis. Right? It is both. It is both a spanning set and a linearly independent set. And this would be for R3. Okay. So this is a basis for R3, but as you can see, as long as this matrix that I get here is invertible, I'll have another basis. I can make lots of bases here, right? So what if I instead, let's say I have an S prime, which is, I don't know, 1, 0, 0, 1, 1, 0, 1, 1, 1, right? So let me write those three vectors down. Right? If those had been my three vectors in R3, I would lay them into the columns here, and I still have a non-zero determinant. This one is upper triangular, right? The determinant of a triangular matrix is just 1 times 1 times 1 here, right? So this is also a basis for R3. In fact, a vector space can have lots of different bases. They are not unique, right? We could go back, just as another example, if we look at P3 of R, right? If we look at P3 of R, we could take the set, sort of what I would call the standard. This is called the standard basis for R3, where you just take literally the power, for P3, you just take the powers of X. So this is often called the standard basis. But you can check that the following set, and I actually did this as an example in the past, where if you just take something like this, so 1, and then 2 plus 3x, and 4 plus 5x plus 6x squared, and 7 plus 8x plus 9x squared plus x cubed, it turns out that that is also a basis. Okay? Again, you would end up, so like if you were to put this one into a matrix, you would just put the 1 there and the x there, right? So this is how you would fill out this matrix. You can clearly see that it is invertible. It's a square matrix that is invertible. This one would be almost the same thing. It would look similar, except this one would just be upper triangular instead. But it is still invertible. That's all that actually matters there, right? So anytime you have a vector space, you can have lots of different bases for it, okay? So just a quick reminder again, right? S is a basis for V if, okay, we already have this, I just want to write it down again, right? S is a spanning set. And secondly, S is Li. Those are the requirements. And we can have many different bases for a vector space. But one thing is common to all bases. There's one thing that both of these bases for R3 have in common. And there's one thing that both of these bases for P3 of R have in common. I'm wondering if you can see what it is. Right? These two bases have one thing in common with each other. They're not the same vectors, but there's something about the bases that is the same. Same thing down here. Not the same vectors in these two sets, right? I guess I could call this one S prime. We don't have the same vectors in these two sets, but there is one thing that they do share in common, and that is the number of vectors that you see there. The number of vectors. So in fact, that is a property that is shared by all bases, the number of vectors. So this is actually a somewhat of a, well, to really prove this rigorously is a little tough. We're not going to do that here. But what I want to say is that every basis for a vector space V contains the same number of vectors. The same number of vectors. They have to have the same number of vectors. And that is called the dimension of V. The dimension of V. So, for example, the dimension of R3 is just 3. Okay? And the dimension of Pn of R, so the dimension of, well, let's start with P3. P3 of R, this was 4. If you go back to those examples that I just erased, right, every basis for R3 has 3 vectors. Every basis for P3 of R has 4 vectors. And in general, the dimension of Rn will always be n. Okay? And in general, the dimension of Pn of R will always be n plus 1. It's always one more than the subscript on the polynomial space. Okay? So polynomials of degree 5 or less would be 6-dimensional. Right? That's kind of what we're saying. What about some other examples? I wonder what the dimension of Mn of R should be. Imagine you had, let's just take a 3 by 3 example. Suppose your matrices were 3 by 3, right? How many variables are you going to have to bust out when you create that spanning set for M3 of R? Well, you can see right here that I have 9 entries in that matrix, and in fact, a basis for M3 of R is going to have 9 vectors in it, right? The answer here in general is n squared. Okay. What about a matrix that's not square? What if it's an m by n matrix? Right. What's the dimension of that? It always helps to look at an example. Suppose it was a 2 by 3 matrix. Right. If I had a 2 by 3 matrix, I could label the entries like this, right? And if I bust out those variables, right, and I look at the matrices that are left, those matrices that are left are going to be your spanning set, right? And they are going to actually be a basis as well. They're going to be linearly independent. And so there are 6 variables to bust out, which means you're going to get 6 matrices that you can look at. And so the answer here is going to be m times n, right? M times n. Okay, fantastic. So there's just a few formulas for you. These are standard. So right here, I guess I should put a box. This is standard information, guys. So anybody in a vector space class is going to need to know these numbers right off the top of their head. Okay? So those are the dimensions of those familiar spaces. Now, just to kind of help you understand why every vector space has to have